Oh, okay. Okay, recording. Okay, all right. So in this video, we are back to EMaths, and we are going to start chapter 10 of EMath. So in chapter 10 of EMath, the title over here is talking about area and volume of similar figures and solids. Right? In 10.1 specifically, we will talk about area of similar figures. So before we start on this, let us recap the previous chapter in chapter 9. So in chapter 9, we talk about congruence, we talk about similarity. Okay, so what is congruence? Congruence means that one shape is identical to another shape. But for similar shapes, right, similar triangles, right, one triangle is bigger than the other triangle. Both of them have the same shape. It's just that the length follow a certain ratio. Okay, so it can be twice as big, it can be 3 times as big in terms of the length. Okay, so one example over here that I want to show you is like this from previously. Okay, so these are two similar triangles, right? As you can see, this form the SSS similarity. So for example, if you notice this one over here, the base, right? This is actually like a times half kind of thing, right? The ratio is times half. The side length, this is also times half. The last length over here, this is also times half. So the ratio is actually half, right? The ratio. So when we talk about similar triangles, right, the ratio is the important word. The ratio of the corresponding lengths are the same, okay, for similar triangles. Okay, so how do we form our relationship is that we can put A1 over A2 is equals to B1 over B2 like that. Okay, or we can actually do A1 over B1 is equals to A2 over B2 also can. You want to flip the fraction also can, as long as it matches. Okay, so A1 match to B1, A2 match to B2, or A1 and B1 match with A2 B2. Okay, so this is the concept that we've learned in Sec 2 and Sec 3, congruence and similarity, especially for similarity. Okay, now in this particular chapter, we'll extend this idea of the ratio of length. These are ratio of lengths. We are extending the idea of the ratio of lengths to area and volume. Okay, so without further ado, right, let's take a look at this activity 1 over here. Now, if you take a look, so from figure 1 to figure 2, the corresponding side over here, the corresponding breadth, right? So what is the ratio? The ratio is actually 2 times, correct? And what about the corresponding length on top? The ratio over here also 2 times, correct? So let's take a look at the area. So for figure 1, the area is 1 times 2. So this would be 2 cm square, right? For figure 2, it is 2 cm times 4 cm. So over here we have 8 cm square. So over here, right, if you notice, the length, the length over here, the ratio is times 2, right? However, if you look at the area is actually times 4, right? So is it a double thing or what's going on? So as you can see over here, the length, this breadth times 2, the length also need to times 2. So in actually what we are doing, right, between the area is over here, we actually times 2 but square. We times 2 square, right? Because each of the length we need to times 2. Okay, so the area 1 to area 2, the ratio of area 1 to area 2 is going to be 2 over 8. This is going to be 1 over 4. And this is going to be 1/2 square. So I'm going to write it like this first, 1/2 square. Right? So you can see that this is one part. So this, you can see that this is 1 part to 2 parts and square, because you're actually having the same factor. Okay, now let's take a look at the next one over here for area. Okay, so the area of a circle, so it works the same way as a circle. So the thing is, this ratio, right, from 2 to 5, right, it is times 2.5, right? Or you can write it as times 5 over 2, correct? But let's check. Okay, let's check the ratio of the area. So area for this is pi r square, correct? pi r square. So in terms of pi, I'm going to get a 4 pi cm square, correct? Pi times 2 square, so 4 pi cm square. Then pi times 5 square, I'm going to get a 25 pi cm square. So let's check out the volume, the ratio of the area. The area is this 4 pi over 25 pi. So if you can cancel off the pi, okay, if you can cancel off the pi, you're just gonna have 4 over 25, and 4 over 25, right, is actually 2 over 5 square. If you look at the ratio of the length, right, the ratio of the length, this is 2 parts, this is 5 parts, correct? And the length over here is 2 to 5, but square, because of the pi r square over here, this square effect, right? So what do we observe over here is that the ratio of the area, okay, so given that the ratio of length is L1 over L2 or R1 over R2 or height 1 over height 2, you can take the length, the radius or the height, right? The ratio of these two lengths, we can relate that to the ratio of the area. So what is going on is actually the ratio of the length, right? The ratio of the length square. Right, so this is the result that we observe from the two activities. Okay, so one more time up. So what is going on is actually, so this gives us a very a good sense of the dimension. Oh, okay, I think I was paused. Okay, so this gives us a very good sense of the dimension. Okay, so over here the length is one dimension, correct? The ratio of the length is one dimensional, but the area, right, the area is two dimensional. So in order for the length to match the area, we need to square it so that we can match the area. So it will be something like this. Happened last year when we were doing map scale. Remember the map scale when we have 1 cm is to 5 km, correct? When we want to convert to an area scale, it is 1 square cm square 5 square km square. We square the whole thing. So similarly over here, the length, the ratio of the length, when we square it, it becomes the ratio of the area. Okay, so this is the full thing that we're going to do this year. So when we have the ratio of the length square, we're going to get the ratio of the area. And on the reverse, if you want to look for the ratio of the length, we just throw the square to the other side. So we will give us this ratio of the area square root or power half. Okay, so without further ado, let us check some examples. So over here we have okay, for part A we have two rectangles, right? So we are looking for A2. We are looking for the second area. Okay, so we are given the two lengths. We now can relate the area. So how do we do this? We just need to set up. So I'm looking for A2. So I'm going to have A2 over A1 is equals to L2 over L1. But because length is one dimension, I need to square. Okay, so A2 is an unknown. A1, area 1 is 32 cm square. Length 2 is 7. Length 1 is 4. And this would be square. Okay, so how do I find A2? Very easy. So A2 is going to be equals to 7 over 4 square times 32. So this would be, so this will give me 98 cm square. Okay, as expected, the second shape is bigger than the first one, so it's 98 cm square. Okay, now let's take a look at B. B is a pentagon, so it works exactly the same way for any shape. As long as they are similar, it works for any shape. So over here, the length is 1 is 6, 1 is 2.5. The area, 1 is 61.9, 1 is the unknown. So we are looking for A1. Okay, A1. So A1 over A2 is L1 over L2, but the whole thing square. Right? So A1 unknown, A2 61.9, L1 is 2.5, L2 is 6, whole thing square. So A1 is equals to 2.5 over 6 square, right, times 61.9. So over here, 2.5 divided by 6 square, then times 61.9. So I'm gonna get, okay, this one no choice, 10.7465. So I'm just going to round this up to 10.7 cm square. So as expected, the first shape is a smaller shape, so we are going to get a 10.7 cm square over here. Right, so this is for examples, practice now what? Practice now 1, examples A and B. Okay, like that. Okay, let's take a look at practice now 2. So practice now 2 requires us to recognize similar figures, alright? So in practice now 2, ABD and ACE. So ABD, right, this one, and ACE, this one is a straight line. BC is parallel to DE. So a very common way to spot similar triangles, right, is like this. When you have a pair of parallel lines in a triangle. Okay, AB is 8.4, so it's given that this is 8.4. The areas are 49 and 100 meters square. Okay, area of ABC, right? Do you see this? And the area of ADE, right? So both of these are similar triangles. Find the length of BD, this length over here. Okay, cool. So over here, right, what we're doing is do we need to show that these two things are parallel? We don't need. Okay, we don't need to show that these two things are parallel. No, sorry, these two things are similar. Okay, because they didn't ask us to do this. But it will be good to recognize that triangle ABC is similar to triangle ADE. Okay, is similar to triangle ADE. So because of this, we can actually match, right, the area of the length to the area of the ratio of the length to ratio of the area. So ratio of the length first. So I'm looking for BD, right? But the triangle that I'm referring to is this one and this one, like this. Okay, so AB, so this is AB, C, ADE, right? So ABC, this is 8.4, right? This is the unknown one. And the area, this is 49 meters square. This one is 100 meters square, like this. Okay, so how do we match this? Okay, so I'm going to do this. So AD over 8.4, right, is equals to 100 over 49. But the 100 over 49 is the area, right? So the length we need to square. Okay, the length we need to square. Okay, now let's do a little bit of thing for AD. Because AD, we know that AD is 8.4 plus BD. So in order for us to look for BD, right, it'll be just nice for us to just do this straight away. So this will be BD plus 8.4 over 8.4, and we just throw the square root to the other side, will give us 10 over 7. Okay, 10 over 7. Okay, so let's do this. So we have a BD plus 8.4. Okay, so we have 10 over 7 multiplied by 8.4, give us 12. So BD is equals to 12 minus 8.4. So it will give us a 3.6 meters, like this. Okay, so BD would be like this. So you know what I'm doing, right? So at this stage over here, right, this is just L1 over L2 is equals to A1 over A2, correct? But the L1 and L2 we need to square. Okay, so this is applying the formula for this part over here. Okay, like that. So there we go for practice now 2. Okay, so let us look at the second type of reverse case, where we have exercise 10A and question 4. So we need to look for the unknown length now. Okay, so okay, I will focus on part D. The rest I will let you try out, but I'll focus on part D. So these two are similar figures. Okay, it's just that one is bigger than the other. Okay, so over here, how do I relate this? Is that I'm looking for D. So D over 9 is equals to the area 12 over 27. So the area over here is 2-dimensional. The length is 1-dimensional. So I will need to make this a square to match the dimension. Okay, so over here I have a D over 9 is equals to square root of 12 over 27. So D is equals to this ratio times 9. So this ratio times 9. So this is going to be equals to 6. So D is equals to 6 cm. Okay, so mainly like this. Now, then for part A, I will let you try on your own. Okay, I will move on to this question 9. So question 9, it is a bit vague. It is a bit vague. So question 9 is the one that we will encounter more frequently. Okay, so over here, let's take a look. We have two solid cones, geometrically similar. So now instead of shapes, we are looking at solids. Okay, so I'm going to like draw, one is bigger, try to draw one is bigger than the other, like that. Okay, like, yeah, okay, something like that. Okay, so just imagine that they are geometrically similar lah. Okay, so the height of the cone is 1.5 times of the other. So means if this is h2, okay, if this is h2, right, this is height 2, and if this is height 1, right, correct? So what this sentence tell us what this sentence tell us is that our what this sentence tell us is that the h2 over h1 is actually 1.5. Okay, 1.5 of the other. Okay, so h2 is 1.5 times of h1. Okay, and given that the height of the smaller cone is 12 cm, now then we look at the surface area, right? The surface area is 124 cm square, right? Find the height of the larger cone and find the surface area of the larger cone. So let us find the height of the larger cone first. Okay, so we have our h2 over h1 is equals to 1.5. So the ratio of length is 1.5. It's already given. So it will be meaningful for us, right, to do this. So to just yeah, so h2 over h1 will be 12. So this is 1.5. So h2 would be 12 times 1.5. So this will give me 18 cm, right? The second one will give me 18 cm. Okay. Now then for the surface area of the cone, now even though the from height to surface area, the relationship is like a bit distance, right? But we can actually, the ratio will still be the same because they are similar objects, they are similar quantities, similar figures. Okay, so for anything similar, the ratio will be preserved. Okay, the ratio will be preserved. So the surface area of the larger cone, so means we are looking at A2, okay, divided by A1. So A2, I'm looking for A2 divided by A1. This is going to be equals to H2 over H1, but we need to square. So A2 is the one that we don't know, right? A2 is the one that we don't know, okay, but we have information from A1, 1, 2, 4. Okay, so A2 over, now 1, 2, 4 is equals to, now H2 over H1, the ratio is 1.5. So I'm just going to put in 1.5 square. So A2 is going to be equals to 1.5 square times 124. So I'm going to get a 279 cm square. So the answer is 279 cm square. Okay, like that. So even though the the area is not like half time space, even if it's surface area, it works the exact same way. Okay, because of similar figures, the area or regardless of the surface area works exactly the same way. Okay. Okay, so for this next example, we are going to look at one example over here, right? For which the shape is a little bit like the area that we're going to find is not so straightforward. Okay, so in the figure we have okay, so very obviously this is a triangle and it is similar to this outside triangle. Okay, so very obvious it's going to be like that. Okay, and BD is parallel to AE, ED is 2 cm, 6 cm. Okay, given that the area of CBD, so this small area over here is going to be 9 cm square. So find the area of this thing. So, but the thing is, in order for us to find this area, we need to find the area of the full triangle first, because the similar triangles are this. These are our similar triangles, right? This is not similar to this. No, cannot. Okay, so we have to use the big triangle to help us to do so. Okay, so let me sketch out the big triangle so that it is like, you know, easier to for us to use. Okay, like that. Let me try out. Okay, so over here I have A, E, and C. I have a B, D, and C. Then I have a 6 cm over here. Now EC is going to be 8 cm. Agree? And area of CBD, so this is going to be 9 cm square. So in order to look for this area, right, we first need to find the area of the big triangle. Okay, so what are we going to do is, now I'm going to look for the area of triangle AEC, and I want to compare it, I want to match it with the area of triangle BDC, like that. Okay, and then this one is going to be equals to the big one, 8 over 6, but this is this is going to be EC over DC, like that. Okay, EC over DC, but square, because the area, the length, right, need to square to match the dimension of the area. So I need area of triangle AEC over, now BDC is going to be 9, EC is 8, DC is 6. Just make sure that the units are same. So area of triangle AEC is going to be equals to 8 over 6 square times 9, like that. Okay, so 8 over 6 square times 9 will give me 16 cm square. But are we done yet? Not yet, because the full triangle is 16 cm square, but we only need this small piece, correct? So technically, last but not least, the area of our ABDE, this shape is going to be 16 minus 9. So 16 minus 9 is 7. So the answer is going to be 7 cm square. Okay, so means we are taking the big triangle. Okay, we're going to take the big triangle minus the area of the small triangle to find the area that we want over here. Okay, agree? Right, 16 minus 9. Okay, so a lot of the times you're going to do things like that. Okay, and one example where you can see that happening is this cone over here. Okay, so I'm going to let you think about this cone later. Okay, as you continue to try. Okay, I'm going to let you think about this cone. Okay, you may need to do some form of subtraction, and more importantly, let me stress again, presentation, very important. Okay, so as we go back and see, I want you to see how I label my stuff. Okay, so the presentation is very important, so that the people marking, right, won't misinterpret what you want to write. Okay, now I'm going to end off this video, okay, with one last concept, but this concept is very important. Okay, so I want you to look at this set over here, very important over here. Okay, now instead of similar triangles, all right, instead of similar triangles over here, now I want you to look at triangles with common heights. Okay, I want you to look at triangles with common heights. So what if the triangles are not similar and the triangles have a common height? So where is the common height, right? The common height is actually over here. This is the common height, 90-degree height. Okay, so do we need to square the length? So what I'm asking for is okay, so the question that we are posing here is the area of ABC over the area of ACD, these two areas okay, so means I'm looking for this area versus this area. Okay, is it going to be 1 over 3 square, because it's the ratio of the length square? Okay, so is this going to happen? So this is the question. Okay, so let's do some calculation. Okay, so the area of triangle ABC over, right, area of the triangle ACD. Okay, so what is the area of the triangle ABC? Is half times base times the height, common height. Okay, area of ACD is going to be half times the base 3 times height, right? Area of ABC, half times base times height. Okay, area of ACD over here, half times base times height. Okay, so let me now do the honors of cancelling this and cancelling the h. So actually, right, it is just 1 over 3. And if you want to compare, right, it is not the same. Not the same. It's not 1 over 3 square. So this one, the answer is false. Okay, so the actual answer is no need to square the length. Okay, no need to square the length. Okay, when the triangles have a common height. Okay, so as long as you can identify the triangle with a common height, okay, you don't have to square the length. We just take the we just take the ratio of their length will do. Okay, because the height will cancel off, as you can see in the working over here. Okay, the heights will cancel off, as you can see in the working over here, right? So the heights will cancel off because it's a common height. So one more time, so when we have similar triangles, you don't have a common height. When you have similar triangles over here, right, these you thought that these are not common height, the heights are different. All right, even if you want to play this 90-degree and this, the heights, the so-called heights are different. Similar triangle is one is big, one is small, and both of them have the same shape. But for triangles have common height, it is one will be this shape, one will be another shape, another kind of triangle. Okay, so it's a bit different. Now same goes to this. If you want to look for the area of this and the area of the full thing, it is actually 1 part to 4 parts, 1 to 4. Okay, so we take note. So one more time, for triangles that are not similar and triangles that have a common height, we don't need to square the length. We just take the ratio of the length because the height cancels itself. So without further ado, let's take a look at practice now 3. So in this given figure, BC is parallel to QR. So over here, right, if you can see, this ABC and AQR are similar. Okay, ABC and AQR are similar. So it will be good if we can extract ABC. Okay, we can extract ABC. And let us extract AQR over here. Let me extract with a bigger triangle, AQR. Okay, similar triangles. So AB is 5 cm, BQ is 1. So this will be 6 cm. PQ is 1 cm. QR is going to be 3 cm. Okay, I don't know BC. And that's about it. Okay, then we have another set of triangles right over here. I have this APR, right? APR. Okay, I have APR and I have AQR. They are not similar triangles, but they share a common height. Okay, they share a common height over here. Okay, so let us find. Okay, so let's be a bit focused and let's try to find the area of APQ. So APQ, wow, this area. Okay, area of APQ. Oh wait, one more. Area of AQR is 21. So over here I have a 21 cm square. So AQR 21 cm square. Okay, so technically speaking, okay, so if you want me to draw this out, okay, it looks something like this, right? Something like this. Okay, like this. And I'm going to draw that common height for you to see. Okay, so A, P, Q, R, 1, 2, 3. Okay, so let's take a look. So area of APQR. Okay, so the area, right, will follow the ratio of the length. So area of triangle APQ. Okay, APQ is equals over area of triangle is given AQR, so I'm going to use AQR. So it's just the length, so it's just PQ over QR. Okay, so I have half base height, but it can cancel off. So if you cannot see, right, if you cannot see, I will encourage you to do half times base times height. Okay, and then half times base times height. If you really cannot see, then you can cancel off the half and the height. Okay, but if you can see straight away, we can do this. So area of triangle APQ over 21 is equals to 1 part to 3 part. Don't need square. Okay, so area of, okay, so from here, area of triangle APQ is equals to 1/3 times 21. So this is going to be 7 cm square. Okay, 7 cm square as the answer. Okay, so for part 2, okay, part 2, let me cut and paste this over there. Cut. Okay, now I'm looking for area of ABC. So the area of triangle ABC as compared to the area of triangle PQR is going to be equals to AB is given, and I'm going to use AQ, the given length, AB and AQ. But because length, I need to square, because these two are similar triangle, they don't have a common height. So I want you to notice the difference between this and this, right? This one with a common height, we don't need to square. Without a common height and similar, we will square it. Okay, so what we have is area of ABC, area of PQR is 21, AB is 5, AQ is 6, and then square. So last but not least, the area of triangle ABC is equals to 5 over 6 square times 21. So I'm going to have 14 and 7 over 12 cm square. Okay, 14 and 7 over 12 cm square, like this. Okay, so this is the end of what I want to do. So on your own, what I want you to do is to try the remaining questions, right? Try the remaining questions over here. Okay, now one last thing for me to reinforce again is this one. For the first one is the area of similar figures, right? When you have a similar figure, one big, one small, the area, the ratio of the area is the ratio of the length square. So think of map scale. Then for ratio of areas for not similar triangle, but they have a common height. Now over here, we just take straight away the area of the ratio of the length, because the height will cancel itself. So we don't multiply in 2 dimensions, we only multiply by 1 dimension. Okay, so just think of it in terms of like this. Okay, so this ends the video for the area of similar figures. So now we settle area. In the next video, we'll talk about volume. Okay, so stay tuned.